Hello, in this video I'm going to go through just a few odds and ends that hadn't fitted into the previous oscillations videos. We had looked at pendulums in previous videos to see that they oscillate with simple harmonic motion. Well, it's the same with a mass on a spring, so let's have a quick look through that because sometimes people get a bit confused with this, mainly what to do with the weight. So there's our mass on a spring. We've got weight going downwards, we've got tension going upwards. So at equilibrium, the tension is equal to the weight at equilibrium. And we also know that that is going to be equal to the spring constant multiplied by the extension. So that's all fine when we're at equilibrium. Well, what happens then when we move away from the equilibrium? Say we've moved the mass down by some distance s, then we can say now that the tension is going to be k times x plus s, which is kx plus ks. So when we're looking at our resultant force, having displaced the mass from equilibrium point, this kx we know is equal to the weight. So we can ignore the kx and we can ignore the weight and just look at the changes in the tension due to displacement from the equilibrium position. So when we plug all of that into Newton's second law, we're going to have that our net force, if we're going to say measure that, let's take downwards as positive. So we've got a positive displacement. So we're going to have a negative net force of minus ks because that's acting upwards. And that's going to be equal to our mass times our acceleration. So we've now got our simple harmonic motion equation. The acceleration is equal to minus k over m times s. And we know that that k over m in simple harmonic motion is omega squared. So omega squared, excuse me, is equal to 2 pi over t all squared, which is going to be equal to k over m. So that means that t, the period of oscillation of a mass on a spring performing simple harmonic motion, i.e. a spring which is obeying Hooke's law, we want that linear relationship between tension and extension, that is going to be equal to 2 pi root m over k. So that's another one of those standard results. You can see how similar that is to the period of oscillation of a pendulum, 2 pi root L over G. So that's what we've got going on with a mass on a spring, quite easy to work out. But as I said at the start, people tend to get confused when they look at, well, what do we do with this weight? It's always hanging around and the tension is always hanging around, and they end up having this really complicated equation for Newton's second law where it just drops out in the fashion just shown. So that's one thing off the list. So that brings us on to damping and driving now. This is where we're adding an extra force into the system. So we're going to be injecting a certain force at a certain point in the oscillation and seeing how this affects the oscillation itself. Now, the easiest way to get the grips with all of this, I think, is thinking about swings. So we've got a person on a swing going backwards and forwards like a pendulum about this equilibrium point. And we know from experience what it's like if you're pushing someone who's sitting on a swing. Well, you've got a number of ways you can do this. The standard thing is you wait until someone's at an amplitude, and we're doing that because at the amplitude they're instantaneously at rest. We've got this zero velocity or speed, whichever one you're wanting to look at. So that makes it easy then, or easier, to inject a force into the system. So if this person's just come up, they're just about to move back in that direction, we add a force pushing them in the direction towards the equilibrium point. Well, that's going to speed them up. If it's going to speed them up, then, well, we know that the period of the oscillation is independent of the amplitude, and it's constant for a particular pendulum, at least at low angle, at small angle. So speeding them up is going to increase the amplitude, but it's not going to change the frequency of the oscillation. So what we're getting on this is we're driving the motion. So we're adding force to the oscillation, which is going to increase the amplitude. So that's what we're doing with driving. With damping, we're well, I suppose one last thing with the driving is, of course, we don't have to actually add this force at the amplitude. You could add it anywhere, but providing it's increasing the amplitude when you add the force, then we've got driving. If it's decreasing the amplitude, then we've got damping. So if you were going to stand here, take some kind of kamikaze position in the equilibrium point, the pendulum comes back towards you, and then you oppose it with a force, then you push it back the other way, then yes, we're stopping that oscillation, or at least we're slowing it down. So we are damping it. We're going to reduce the amplitude. So if this is our displacement time graph for a particular oscillation, which is just going along, typical sort of sine wave approach, if we're going to damp it or we're going to drive it, we're not changing the frequency, because as we know, the frequency is we got a 2 pi root L over G for the time period. So this just depends on the length of the pendulum, which we're not changing. So the frequency isn't going to change. But if we're damping it, it's just going to be the amplitude is going to decrease and decrease. And if we're driving it, then it's going to get bigger and bigger and bigger. But these are all meant to be intersecting at the same point all the way along. This is the same frequency. So we've got one amplitude going outwards and we've got one amplitude going inwards, increasing, reducing. So that's all we've got with damping and driving. There's a little bit of terminology around the damping. You can have light damping, as in it's a slow reduction in amplitude. We've got heavy damping. It's a much sharper reduction in amplitude. You've got critical damping. That's where you're just killing it dead, really. You're just taking it back to the equilibrium point. You're stopping the oscillation completely. So it won't pass through equilibrium anymore. It will just go back to equilibrium. And that's your critical damping. So just be sure not to mix up critical damping with heavy damping. Heavy damping, it will keep oscillating, but the amplitude will drop rapidly. Critical damping, you're just taking it back to equilibrium. So that's what's going on with damping and driving. It brings us to the last point of resonance, that if you, sticking with the idea of the pendulum, we've got this time period of the pendulum, as we know, there's 2 pi root L over G. So if we keep driving at the same frequency, if we keep pushing at that amplitude every time and reinforcing the motion, then the amplitude will just keep on increasing all the time, providing we're in sync with the natural frequency of the pendulum. So the natural frequency is the frequency associated with this time period. So F0 is 1 over T. That is our natural frequency. So if the natural frequency is equal to the driving frequency, I suppose really it's the other way around. We're given a driving frequency that's equal to the natural frequency. So really we're thinking of this as the other way around. But yeah, so we're driving at that natural frequency. Then we're going to get resonance, where the amplitude is just increasing. So they get us often to draw these sort of graphs in exams, where you have the driving frequency on the x-axis. You've got the sort of the amplitude that's produced on the y-axis, and when we hit F0 as our driving frequency, then in theory we've got this asymptote going on, that we're going to have this infinite amplitude. Now in reality that doesn't actually happen, because you're always going to get some kind of damping going on. You're never going to have a system which has got no friction in it whatsoever, and friction acts to damp, because friction always opposes the motion. We know this. So friction is a damping force, which means this is going to cap off at some kind of peak in reality. So yeah, in reality it's got a peak. In theory it's got an asymptote at F0. and that's what's going on at resonance. Now, the more you're damping the resonance, the more you're damping anything, of course, you're reducing the amplitude. So you'll get various, you could draw a lot of lines on here. So if I'd drawn it with the asymptote, then you could say that is no damping at all, would be the asymptote. Then you've got light damping, might look like what it is at the moment. If you add heavy damping, then it's gonna reduce it a little bit, and I'm going to get onto what I'm doing with that peak in a minute. And the more you damp, the more it's reducing this effect of the driving frequency. You're still going to get an increase, you're still going to get a peak at a certain location, but that peak is going to be much reduced as we go through this no damping, which is just theoretical, light damping, heavy damping. So all of the line must keep on dropping all the way down. You can't have any crossing of these lines on these graphs here. You'll also notice that I've moved the peak. It's sort of moving off to the left here. Yeah, I mean, if you think of what's going to happen if you start damping a system, I mean, in the theoretical case, we're not going to be changing the natural frequency. But you start getting clouded again when you get into the real world. If you're slowing something down, if you're adding a force that is opposing the motion, then you can't be making it go quicker. I mean, everything's going to be slowing down, in which case you're going to get a greater time period because everything's taking longer, in which case you're going to get a lower natural frequency. So the more you damp something, our natural frequency is going to move off to the left here. Damping means a reduction in natural frequency, which means our peak is going to move to the left. Now, again, it's one of those ones in theory, you sort of get caught between two stools on this, that but you can say, well, in theory, yeah, the natural frequency is just to do with the geometry. It's just to do with the setup of the pendulum. It's not to do with anything to do with the forces. But as soon as you get into the real world, well, those forces are changing the time period, which is changing the frequency, which is changing your natural frequency. So the peak moves to the left. But you don't have to get too bogged down in that sort of thing. It's more about what's happening here with the resonance as to why we've got this peak, and then what happens if you've got a damped system that's being driven. Because of course, this driving frequency it's not a damping frequency. It's a driving frequency. It's an input force that is designed to, or at least will, even if it isn't designed to do so, but it will increase the amplitude. That's the whole point of a driving frequency, to increase the amplitude. But you can still damp a system that's being driven, such as by adding friction to it. So you're still driving it, you're still pushing the swing in order to increase the amplitude, but the rusty chain that is hanging on is adding friction to the system. So it's driven while also being damped. So you can have both things going on. And that's why we're drawing these multiple lines on here. All of these are being driven, but you've got more friction, say, more damping in the system, which is why these lines keep reducing and why the natural frequency shifts over to the left. So yeah, I think that's tied up the loose ends really in oscillation. So that brings us to the end of a topic. There's quite a lot in this topic, but we'll go through a lot of example questions now. Get used to your calculus, how we can describe SHM with calculus, because quite often they don't do enough of that in physics books because they don't want to assume that you know how to do the calculus. And keep an eye always on that link with circular motion. Tying the two things in together really does add a lot of power to your understanding.